In the morning. So you see those paths getting shorter as the atmosphere gets lower, and then things stabilize. And then as the evening comes on and the ionosphere starts to become less dense, it raises up and the propagation paths get longer again. And so you get this negative frequency shift here.
What's that peak there?
That's an excellent question. I'm so glad you asked. You've got good eyes over there. So yes, what is that peak there?
Sundown.
What's that? It is not sundown. So remember these X-ray flux plots? So this is another GOES X-ray flux plot. This is not the plot I just showed you like 2 minutes ago. This is the one that corresponds with August 20th. And you see there's a little M-class flare over here. So that is what corresponds with this here. So I think you had a sudden flash of ionization associated with that flare. It shortened the propagation paths up, and you see the sudden spike in the frequency from WWV. Isn't that cool? Yeah. Yeah, Steve sent some really beautiful measurements, and I'm actually looking much more closely at his measurements right now. And so here's what he sent for the eclipse. Yeah, okay. Yeah, so this is all Steve's work here. He sent this to me. But again, you see some of the same basic features we saw in the previous one. Say in the morning, you see the positive frequency changes. In the evening, you see the negative frequency changes. But right here in the middle, this is the eclipse section. And you know, if you think of the beginning of the eclipse as like going into evening, you'd expect this area to kind of match what evening looks like. And does it? Yeah. And if you expect coming out of the eclipse after totality, you expect that to look kind of like morning. Does it? Yeah. So that's really, really good. So these are great measurements. Now, does anyone see another really interesting feature here? Yes? Right.
Why are those hours what they are?
Well, it's 90 minutes for totality to move across the entire United States. It was actually about 4 hours for the start of partial eclipse to hit the United States to the end of partial eclipse to leave the United States. Right. So that fits much better. So yeah, so you can think totality is this big visual thing that everyone talks about, but what actually affects, say, the ionosphere happens over a much longer time scale.
Why is the magnitude of the changes greater on this day? Or is your 0.3?
Why is it higher on this particular day? I'm not fully sure. That's something I still need to look into. Yeah. So I don't really know the answer to that right now. But the thing that, yes?
If you go back, yeah. The question I have is, notice the two negative plots. They're like mirror images of one another. Why does this start much lower in the first drop and higher in the second drop and then go lower?
Where is that?
At 21 hours DC.
Okay.
You've got suddenly an area of positivity.
Right, over here.
Well, no, I'm thinking about the negative drops. Okay, you see where they drop negative?
Yes.
The first one, notice that the first drop is corresponding to the end of the second drop in the second group of negative plots. That's peculiar, and I'm just wondering why that is. Why do they start out low at the first and then go higher towards zero, and then in the second start like near zero and go deeper?
Yeah, that's also something I'd have to look into a little bit more. So you're saying why does it go down here and then go up and then go down again?
Yeah, the two drops are like mirror images of one another. Why?
This one here or that one there. One possibility is you might have a traveling ionospheric disturbance go through. So you can have waves that go through the ionosphere that have periods of, say, 15 minutes to an hour long. That's about how long it is between here and there? Yeah, and those waves can cause a focusing and a defocusing of the HF radio waves. So there could be a traveling atmospheric disturbance moving through here on top of that normal effect that might cause that mirror image. So I'll be happy to show you some other examples after the talk. Okay, but one of the things we're kind of interested in, and another thing I don't have an explanation for at the moment, is this interesting S-curve right at eclipse maximum. And that's actually something I've spent all day today looking at. So if you have any other ideas, I'll be happy to hear them. Yes?
The eclipse maximum that you pointed out, that's eclipse maximum on the path between Milwaukee and Fort Collins on that line?
Yeah, so that eclipse maximum is the one that's right here along the eclipse track. That's the time he used for that. So he just took the Google map with this is the ground overlay, and he picked off that number, and it fit his figure very well. Okay. So another example that someone has sent in, so that was one of the best examples of like a really fine measurement we have. Another example that someone sent in is actually from the father of one of my friends who's a radiophysicist up at the MIT Haystack Observatory. And this is Mr. John Erickson, and he also listened to WWV from Schenectady, New York, and he was listening to both 10 and 15 megahertz. And he, instead of using really fancy frequency measurement equipment, he just took an old Panasonic RF4900 shortwave receiver and recorded the signal strength off the S meter every 10 minutes during the eclipse at both 10 and 15 megahertz. And that generated these curves over here. And so on 15 megahertz, we can see that the signal-to-noise ratio is relatively steady, a little bit of variation. And then as we get towards eclipse, it dips down. And then as you come back, it recovers. And so we believe the reason for this is that the ionosphere has gotten weaker, and the 15 megahertz band just shuts down. More of those radio waves escape into space. On the other hand, on 10 megahertz, that one is more prone to D-region absorption that happens during the day. So when the eclipse comes, the D-region absorption goes away, but this particular frequency is still below the critical frequency even when the eclipse is happening. And so you see an increase in the signal power until things drop off and you go back to after the eclipse. Now here, this plot is from Phil Erickson, his son. Here they plotted the local maximum, so you can see that we're seeing these effects before the local maximum as opposed to the middle. So that's another rather nice example of how you could see some of these effects in just a simple listening experiment. It's very nice. So for the Solar Eclipse QSO party, as you know, this was a contest-like event. We had 2 points for CW or digital, and the reason for that is we were relying on things like the reverse beacon network and PSK reporter to observe the signals, and they do well with CW and digital, but we don't have good automated phone spotting networks yet, so maybe that's something that can be developed. We have 1 point for phone, and we are multiplying the score by the number of grids that you send in. And the exchange is the RST in the 6-character grid square, and I already talked about some of the data sources. And people submitted to HamSCI.org/SCQP, and we are still working on scoring these things. It's been a challenge. I have to admit, I've been working on just the scientific part of this first, and I'm on the hook to present the scores at the Dayton contest dinner, so I will make sure that those are scored by then. Here's the number of observations we got from each of the networks. So both the Reverse Beacon Network and WhisperNet provided over 600,000 spots from each of those networks. All right? PSK Reporter provided over 1.2 million spots. And the participant logs, over 31,000 reported QSOs in the logs that I was able to parse through. So that's very good participation. That's really, really wonderful. Here's some more numbers. I was able to parse 593 logs so far. I found over 5,000 unique call signs in these logs, over 650 4-character grid squares, and 81 DX entities just in the logs, not looking at the Reverse Beacon Network or PSK reports. So these numbers are just from the logs. And here's a photo of when I was operating down in Gilbertsville, Kentucky. And then these are some of my students and some of the people I work with operating at the Jenny Jump Observatory out in Hope, New Jersey. Yeah. So here is a movie of all of the data, okay? So if you aren't sure about the numbers I just posted, you can count all the little dots here and make sure that they're right. All right? So I'm going to play the movie twice, so you have 2 chances to count all the dots. But the color bar here, the blues are going to be your 3.5 and 7 megahertz, and the greens are your 14 megahertz. And we've got this SEQP logs in this quadrant, WhisperNet in this quadrant, PSK Reporter in this quadrant, and RBN in this quadrant. And these are the midpoints. So if I have a transmitter and a receiver, I'm plotting the point in between the two because that's where I'm assuming the reflection is off of the atmosphere. So I'll play this a couple times. So it's a lot of observations. So one of the big challenges here is really trying to figure out how do we crunch all of these numbers and make some sense out of this and hopefully get something new. I'm going to play it again. You can focus on the RBN. I think what you'll be able to see is you'll be able to see that as the shadow comes through, the green dots, the 14 megahertz ones, are going to become less, and you'll see more of the blue 7 and 3.5 megahertz dots, especially in the RBN quadrant. That's when it's easiest to see. And I'll show you some other plots later that are more convincing, I think. So right there, you can see the green ones wipe out a bit and a few more of the blue ones come in. Do that one more time. So we have a few other ways we can look at the data, or we have been looking at the data. One of the ways is just the simple time series. And so these are the number of spots from the Reverse Beacon Network over time for each of the different bands. And the regions that are partial here, gray and partial, those are the regions where there was partial eclipse somewhere over the United States, over the continental United States. The region in the middle is the time where totality was somewhere over the United States. And then it's color-coded by band, so you can see the orange is your 20-meter band. The blue here, this is your 40-meter band. The green is 80 meters. Red is 160 meters. And then you have a darker blue and black down here that's 10 and 15 meters. And you can see very clearly when the event started and when it ended. There's a very nice just shoot up in activity and drop off over there. And you can see that the 15 and the 10-meter bands, they were pretty much shut down both before and after the event. So being at a low point in the solar cycle, they just didn't work very well. But all of the other bands 160 through 20 meters, gave us some interesting information. So 20 meters is the band that started out being beneath the maximum usable frequency or beneath the critical frequency of the ionosphere for most of the United States. And then during totality, it really took a hit. So you can see just number of spots just climbed here, and these are reverse beacon network spots, CW spots. And then you start seeing it drop off, and then in totality, it cuts off, it levels off a bit, and then you see some recovery toward the end. For the 40-meter band, you see things look kind of flat, but you do see a little bump there. Do you see that bump? And that's where we expect the D region absorption to be going away, but the band still to be opening up quite a bit. And then the 80 and 160 meter bands, you see after the middle of totality, then you see a big bump over there. One of the reasons I think we see the bump more after totality here is I think if you look at the distribution of the spots where people are in the United States, there's a lot more people on the East Coast than there are, say, on the West Coast. And so this happened later in the day. So I think this is really when totality came over, say, the East Coast. Here's yet another way of looking at those spots. This is like the maps you saw before, except we have just reverse beacon network, and you can see before, during, and after the eclipse. And you can see a little bit better kind of how the green 14 megahertz spots, they kind of dissipate a little bit more, and you start to see a few more of the blue ones there. It's a little tricky to see, especially on the projector. If we look at one particular RBN station, this is WE9V in Wisconsin, and this is one of the best performing reverse beacon network receivers. Especially, I searched all the reverse beacon network receivers. I tried to find the ones that had matching pairs that heard other transmitters almost continuously from the beginning of the SEQP to the end of the SEQP. And this one had these 10 traces that were almost consistently available through the SEQP. And this is all of those signal-to-noise ratios plotted on top of each other. And you can see, again, as you go into totality, so, and this is the midpoint totality, that line there. As you can see, as you go into totality, you get a hit on the 14 megahertz signal-to-noise ratio, and then as you come out, you get a recovery of the 14 megahertz SNR. To try and look at all of the bands at one time in a way that you could see something useful, I also did what's called a superposed epoch analysis. So I looked at all the data from the reverse beacon network receivers in the United States, and I picked out the ones that looked like they actually had a reasonable amount of observations. And so these are the ones I've picked. I think there's about 60 stars on this map.
This is US and Canada, correct?
Yes, there's some Canadian stations in here as well. So there are a few Canadian stations too. So you can see most of them are clustered on the East Coast. There's a few in the Central and a few on the West Coast as well. So that's the main distribution. And if I take, say, all of the spots from the 14 megahertz 20 meter band from all of those stations, and I put them all into one plot, and I create a spot density plot, I get something that looks like this. So on the y-axis, I have decibels, signal-to-noise ratio, as reported by each reverse beacon network receiver. And then I have hours from eclipse maximum for that particular receiver. So 4 hours going out this way, 4 hours going out that way. And then I have spot density. So the dark reds here are about over 2,000 spots per unit area in here. So it's a pretty high density number of spots. You can really see the general behavior of the 20 meter band during the eclipse. You have this is when things were heating up at the beginning of the SEQP, and then about an hour before the eclipse, you start to see the 20 meter band die down, down to totality. There's a little increase right there, and then things are kind of dead a little bit after, and then about 45 minutes after the totality, you start to see things recover. Not fully recover, but you do get a recovery there. And I looked at, so far I've looked at not only all of the stations put together, but I've also looked at all the individual stations, and I've looked at different combinations of, say, just the East Coast, the West Coast, Central. And this is generally the pattern you see at all of the receivers. So I'd say that this is a very good representation of the general behavior you see of the 20-meter band during this past eclipse. Now, we can also plot, instead of the signal-to-noise ratio on the y-axis, we can also plot the great circle path between the RBN receiver and the transmitter that was heard. And so here, the y-axis goes from 0 up to 3,000 kilometers. So you can see for most of the SEQP, most of the signals were between about 500 to 2,000 kilometers away. And I tried restricting this mostly to about single hop here. I think this is mostly single hop propagation. If you extend it out, you can see some DX as well. But just trying to understand the basics, we were looking between about 500 kilometers to 2,000 kilometers. Again, about 45 minutes before totality, you start to see things drop off. And then about 45 minutes after totality, you see things recover. Any questions so far? Yes?
Can I have a picture of like somebody transmitting the S unit before, during, and after?
Yes, I showed one of those before. That's an example. These are 10 different stations. This is before, during, and after. And that's signal-to-noise ratio as reported by the reverse beacon network. And then this one is signal-to-noise ratio from all of the stations in the reverse beacon network, all put into a 2D histogram. So if you want to see what all of the bands looked like simultaneously, that's this plot over here. Okay? So now this column on the left, this is the signal-to-noise ratio column. The column in the center is the distance, or the great circle path distance column. And then this column over here is the number of spots heard per unit time over the whole thing. On these, the y-axis goes from 0 to 75 dB. And here it goes from 0 to 3,000 kilometers, just like in the bigger plots I showed you before. So each of these is like a small plot, very similar to the bigger plots I've just shown you. And it's organized so the top here is 10 meters, then 15 meters, 20 meters, 40 meters, 80 meters, and 160 meters. And the time, again, is -4 hours to +4 hours. So it's like a matrix of all of these plots. And so now what you can see is, like I said before, we didn't really get any useful information from the 10 or 15 meter bands. You just kind of see splotches, but nothing really coherent. And then you have the 20 meter band, which I showed you the bigger plots of before. You have about plus or minus 45 minutes from the eclipse where you just have a drop off. And then for the lower bands, 40, 80, and 160, you actually see enhancements in the propagation, both in the signal-to-noise ratio and in the distances that you're able to communicate. So here you can see the 40-meter band. You start off about 500 kilometers, and then it opens up to about 1,000, 1,500 kilometers here during totality, and then it drops off again. And then if you go down to the 80-meter band, you see similar types of behavior in the 160 band. And you can see that the lower you go in frequency, the shorter the opening, the smaller the opening is. It doesn't last as long. So it seems like the winning bands to be on before the eclipse was 20 meters, and then during the eclipse was 40 meters. So that's how that wraps up there.